Alright, so first things first, I would like to start this off. No, you got move. Please move. I'd like to start this video off by apologizing for not having my calculus artifact in sooner. I thought that a game would have been cool, and I've spent the past couple weeks trying to learn a program called Python through a friend of mine from Singapore, and it is proving to be a lot harder than I thought it would be. So I would like to apologize. However, I'm still going to work on the game, and if I do manage to finish it, I do want to show you by next year, because I think a game that gave you a tutorial into calculus would be cool. That being said, I still need a calc artifact, and I'm pretty sure that today is the last day, or tomorrow's the last day I can turn something in, according to Mr. Rothenbach, who said I can do my web assigns by today. I only have 2 left. Can you stop, please? Can you, Shep? Shh. It's okay. It's okay. Who's a good boy? I'm distracted. So, I would like to start this off. Calculus, it's not easy. However, the basics are pretty easy, and I'm going to... I'm going to give a tutorial on... Did I start the recording? Yeah, I guess it's recording. I'm going to give a tutorial on the basics. I'm going to start with derivatives. So taking derivatives is pretty easy. If you take a derivative, it can show you things like mins and maxes and general extrema on a graph. Depends on how big the number is, but we'll start off with the basics. So addition, right? Well, actually we'll start off with exponents. So I've got x to the 4th, right? I don't know if you can see that. Essentially what you're going to do is you take the exponent, you put it in front of the variable, and you subtract 1 from the exponent, right? So x squared, the derivative d of x, because that is how you take derivatives of the variable x, would be 4x to the 3rd, right? So you've got that. However, you may be wondering, what if my variable has an exponent of, I don't know, what if it's a root? What if it has a variable of 1/2? Well, it's a similar concept. You've got x to the 1/2, which is equivalent to root x, and you still subtract 1. So now you have 1/2 x to the negative 1/2. You still just subtract from the variable. It's pretty easy. And yeah, addition and subtraction. So now let's say you had x to the 3rd plus 2x squared minus 5x plus 1, right? Well, 1 right here, the 1 right here actually has a variable of x to the 0, right? So any more makes it disappear. So 1 or any constant, right? It could be 5. You know what? We'll make it 5. Plus 5, it goes poof. It becomes 0 because you take the exponent, put it in front. So that's now 5 times 0 times x to the negative 1, and anything times 0 is just 0, right? And then we do what we did before. So we got 3x squared and then since this has a constant right here, you actually multiply the constant by the variable. So that is 4x, and then x to the first is now x to the 0th, so we have minus 5, right? That would be the derivative of a longer function like that. Now, there's something called integrals, which essentially reverses derivatives. This is still just the basics, and so in order to do an integral, you would actually do the opposite. You would take, and you can evaluate an integral from 2 points. That is pretty easy. So we'll evaluate the integral of this function right here from 1 to 3. I mean 0 to 3. So we're setting up the integral. So that would be how you would set the integral up for this function. So then in order to take it, you reverse your steps. So because we subtracted 1 from the exponent, and then we multiplied the variable by the exponent, we will add 1 to the exponent, and then we will divide the variable by the exponent. So 3x squared becomes x to the 3rd, and 4x becomes 2x squared, minus 5 becomes minus 5x. Now you may be wondering, there was a 5 before, right? Well, you're right. And in order to account for that, we add c, right? I don't know if you can see that, but that's c added to the function. C, it doesn't matter what c is for evaluating an integral. There are ways to find c that are a little more complicated than what I'm going to go over. But c cancels out when you're evaluating an integral, so it doesn't even matter. So, and then we now put 3 in. It now becomes this equation right here, evaluated at 3, minus that equation evaluated at 0. So I'm going to show you how to do that. It becomes 3 to the 3rd plus 2 3 squared. That is an alarm to go to school. That was loud. Minus 5 3 plus c minus 0 to the 3rd plus 2 0 squared minus 5 0 plus c. So the two c's subtract, they cancel out. So we're left with this up here because the second half is evaluated at 0, and this will actually give you the area under the curve, which is the other side of calculus, which will give you the total. If you're in physics and you're looking at velocity, and you take the integral of velocity evaluated from 0 to 3, that shows you how far a particle traveled from 0 to 3. So integrals are pretty interesting. So then that would be 3 squared is 27, plus 18 would be, that's 35, 45, minus 15 becomes 30. So this integral has a value of 30. So that is basic exponents. Now you can multiply, you can take the derivative of a multiplication function. That is pretty interesting. You actually will, well, I'll show you on paper, but you will take the derivative of the first function and multiply it by the second function, and then add it to the first function times the derivative of the second function. So we'll do this as maybe x squared plus 5, 3x to the 5th, right? I don't know why these are the functions I picked. I just want to keep it easy because this is supposed to be a tutorial for beginners. And so this would essentially become, the 5 cancels out as we know from before, so when taking the derivative we will do 3x to the 5th times 2x, right? Because that is, if we gave these f of x and g of x, this becomes g of x, f of x, plus f of x, g of x. So this is essentially what we're doing at the bottom. I will have to leave soon. So then this gets added to x squared plus 5 times 15x to the 4th. So that is our derivative, and we can always reverse that. There are ways to reverse that. In this case, you might end up using something like u substitution, which I can't think of a u substitution problem on the spot, and I didn't have one prepared beforehand. But essentially, u substitution looks at, hey, this is a really hard integral to evaluate. In fact, I'm not too sure I can evaluate it. Can I substitute x for u? And what you would do is you would find a function, you would find the derivative of the function, and you can take the function out at the cost of also taking the derivative out. So u goes in for the function, so if it's like x to the 3rd, it's now u. However, you also have to be able to take out 3x squared from the function, 3x squared dx, because that is replaced by du, which allows you to evaluate the function. So that would be substitution. You would mostly use it for multiplication. I will continue this video when I get home. Alright, so I am back. I think I left off with u substitution. So I guess a u sub problem, I explained it as you use u to make it simpler. So here's actually an example. I am taking the indefinite integral, so it doesn't actually have a value because that's just easier to represent it as. It's going to be I guess I'll make it x to the 3rd to the 2x squared, because I don't know, that's the only thing I can think of right now. So here's the problem. I don't know if the camera's pointing at me. Yeah, here's the problem. Essentially, I can look at this and I could be like, I don't know how to integrate that, right? So I would take a variable. I would take a variable. In this case, I'm going to use x squared, and I would have u equals x to the 3rd, right? So then I would take the derivative of that, so du equals 2x squared dx, right? I can substitute that in, and now my equation becomes the integral of, is that really just, that gets taken out. Yeah, that's just the integral of u du. So I have the integral of u du. Now if it was a case where like it was let's say 6x squared, right? I would then put 1/3 in front of the integral to make up for the value that was absent from the integral. So you can easily make up for that. You just put it in front. You're too needy. You know that? You are really needy. Stop. Please, please. So then you would evaluate this. You would evaluate this integral. Okay, Shep, you're really needy right now. You would evaluate this integral, so I would get 1/2 u squared plus c, right? However, it's still as u, so you would then substitute x in, so that gets you 1/2 x to the third squared, which would be 1/2 x to the sixth, plus c, of course. And yeah, that would be u substitution, which you use for mainly multiplication problems, but wherever you can use it, it's good to use it. I've got my dad being annoying and moving my stuff everywhere. Right, fine, here. You're being annoying too, you know that? You're being really annoying right now. So then I guess it would be, go lay down. Next would be, I guess, division derivatives. I'm just going over the basics. I'm not going to go over inverse trig because that mostly has application into Calc 2, even though we've used it in Calc 1. I'm not going to go over rotating. I'm just going to go over how you use derivatives and how to find them, because this is just supposed to be a basic calc tutorial. So if you're taking the derivative of a division thing, so you've got like f of x over g of x, right? To take the derivative of that, so d of x, it would become the derivative of f of x times g of x minus the derivative of g of x times f of x, right, over g of x squared. So in this case, we could do x squared over x plus 1, right? So that would be kind of annoying to do long division, but you could do long division, make it easier on yourself. We're going to take the derivative of that. So that would be 2x times x plus 1, right, minus 2x, because the derivative of x plus 1 is just 1, and 1 times 2x. Not 2x, times x squared, my bad. Times x squared is just x squared, right? And then we're going to put that over g of x squared, so that's x plus 1 squared. And we're going to multiply this out. So multiplying this out, we get 2x squared plus 2x minus x squared over x squared plus 2x plus 1 equals x squared plus 2x over x squared plus 2x plus 1. So that is the result of our division derivative. That's how you take division derivatives. Next, we're going to go over trig. So, and by trig, I guess I'll go over all of the trig. But I'm thinking, because I just remember, I mean, I remember all of trig. I just don't remember how I would explain it. I guess we'll start off with the basics. The derivative of sine x is cosine x. The derivative of cosine x is sine x, right? Negative sine x. So the derivative of sine x equals cosine of x. The derivative of cosine of x equals negative sine x. So here's our lovely problem. However, it does sort of follow exponent rules. So let's say it is sine x squared, right? That becomes cosine x sine x because you're really subtracting 1 and you actually put the 2 in the beginning, so it becomes 2 cosine x sine x, etc. If it's sine to the third, it becomes 3 cosine x sine x squared. That is basic trig derivatives for the first two. Tangent, the derivative of tangent is, yes, so the derivative of tangent is secant x squared. So tan x equals secant x squared, right? And likewise, the derivative of cotangent is negative cosecant x squared. So those are the two derivatives, follow the same rules. So like if it is cotangent squared, it'd be negative cosecant squared x times cotangent multiplied by 2. Same rules, right? And they also, it literally, taking the integrals is a little bit different, but it follows the same thing. You can just reverse them when taking the integral, and it makes things a lot similar. You can also substitute values in for some trig, like secant x squared. I mean sine x squared, because it is a bit harder to take those integrals. But that's why you have u substitution. That's why you also have something called parts that we're going to go over in a minute, because parts is another part of this. It's another integral process, but it mostly relates to chain rule, which I'm going over in a minute. So then finally, the final trig derivatives would be secant x and cosecant x. So the derivative of secant x is going to be tan x secant x, and the derivative of cosecant x is negative cotangent cos x cosecant x. So this is tan x secant x. This is negative cotangent x cosecant x. Right? So here are those two. Follow the same rules. So like secant squared x becomes tan x secant x squared times 2. It follows the same rules, same gist. Yeah. So final thing I'm going to do is chain rule and parts. Parts is a little bit harder. You're pretty much only going to use it with, oh, I forgot, natural log of x. We'll do natural log of x first. So the natural log of x is interesting. The derivative of it is, let's say, and we'll use natural log of x for this case, right? So the derivative of a natural log is going to be based off the function inside of it, and it is actually the derivative of, oh man, I'm going to better represent this, ln of f of x, right? so here's a better representation. I hope you can read that. And we're going to represent this more easily. So with the f of x, the derivative of the natural log of f of x is going to actually equal the derivative of f of x over f of x, right? So, yeah. So this is an example of chain rule, actually. So I probably should have did this after chain rule. However, essentially, you're taking the derivative of the function outside, which the derivative of natural log puts the function inside of it on the bottom, in the denominator of a fraction. And then you take the derivative of the function inside, which is why the derivative of f of x is on top. I will explain that better in a minute. But a good example of this would be, or like with numbers, the natural log of x equals 1 over x, right? We know the derivative of x is 1, that's why 1 is on top and x is on the bottom. We're going to go over chain rule now, because we are not doing inverse trig. Inverse trig is not really something you need to know, and it is kind of more complicated. I'd have to rewrite the proof because I don't remember how to figure it out. I just memorized them. And for logarithms, not natural logarithms, you're never going to use them. I would also have to rewrite the proof for that, but I do have a proof for that as well in my journal that Mr. Z has, because, but you're never going to use logarithms. You're always going to use natural logarithms because it's so easy to convert a logarithm to a natural logarithm, and natural logarithms are so much easier to use that you're just never going to use a logarithm. But we're going to go over chain rule. So chain rule essentially says, I've got my function f of x. However, my function f of x is actually g of x, right? So we'll represent this as f of g of x, right? So the derivative of this would be the derivative of f of x, f of g of x, right? Times the derivative of g of x. Now, that might seem a little confusing, so we're going to do a better representation. We're doing d of x, or the derivative of x, 3x plus 2 squared, right? So we're going to pretend the inside of this is a u, right? So we know the derivative of u squared is 2u. Right? However, we're going to resubstitute this back in for u. So far we have 3x plus 2. Right? That's what we have so far. That is the derivative of f of x, which x being g of x. However, we also have to take the derivative of g of x. So the derivative of 3x plus 2 is just 3. So then we multiply that by 3. So this becomes 3x plus 2, which becomes 18x plus 12. And that is the derivative of 3x plus 2 squared. That is chain rule. It's like nesting dolls, right? You take the derivative of the outside function while keeping the inside the same. And then you take the derivative of the inside of the function and you multiply it by the outside of the function. Now that can be a little bit confusing when it comes to integrals, which is how we get into parts. Parts is the last type of integral we're going to go over, because usually you can just, an integral is just going to be reversing the steps. So you should be able to easily recognize the derivative, because usually it's going to be like addition, subtraction, and we already learned with addition and subtraction. Did we actually? Well, I'm going to go over this anyway. If there's like addition in the problem, you evaluate each part separately. So like, if it's x squared plus x, yeah, I did go over this. X squared plus x would be 2x plus 1. Shep, why are you like this? Why? You're a good boy. So we're doing parts. So we're going to do parts with natural log. So we're going to essentially integrate the natural log of x. So the way parts work is I've got my function. However, my function can be split into the integral of u dv, right? Where dv is one part and u is the other. And then that gets me u times v minus the integral of u minus the integral of v du. So this could look like a couple things, because there's one where it's infinite and you have to do something else. A standard one might be, would that be a standard one? Yes, it would. It might be the integral of x sine of x dx, right? So in this case, we would make u equal x, right? And then we'd actually take the derivative of x. So du equals dx, because the derivative of x is 1 and you keep dx. So then dv would be sine x dx, right? And we take the integral of sine of x, and we get negative cosine x. So then v equals negative cosine x, as we can see. So then this becomes u dv equals uv minus the integral of v du. That's the standard form of this, and we're going to use that to integrate this. So according to this, the problem becomes negative x cosine x, right? Negative x cosine x, because that's u times v, minus the integral of cosine x. But since you can put the coefficient on the outside of an integral, so if you're integrating 3x squared, you can actually integrate 3 times the integral of x squared. The negative from negative cosine x goes on the outside, so we're actually adding this together, as you can see, and we're taking the integral of cosine x dx. This one is not a repeating function. Neither is the natural log of x, now that I think about it. I don't know a good repeating function I can do. Oh! That is a big part that I missed. But I don't know a good repeating function I can do off the top of my head. It would probably have to do something with e of x and trig. Essentially, in that case, you end up having to do parts again, and then you end up with the same function from the one side being subtracted. So then you add that to both sides, you get 2 whatever the integral is, and then you can divide it by whatever, and it ends up working out. That's a bit more complicated, so I'm not going to go over that because it's not basic derivatives and integrals. But in this case, we take the integral of cosine of x, and we get the integral of x sine x dx equals negative x cosine x plus sine x, and we gotta add c to the n to account for any coefficients or constants, and there, that is parts. It follows the same process as up here. We just integrated the integral of v du. In the cases, as I said, where that doesn't work, you actually end up with another parts where u dv is being subtracted from it, and then you add u dv over here and you get 2, and yeah, it's not easy. And since I'm just doing the basics because this is supposed to be beginner's calculus, I'm not going to go over that. The final thing I'm going to do is derivatives of exponentials. So we'll start with e of x. E of x, I could go through a whole proof for this. I have a whole proof for this, actually. It's in a notebook. I don't even have my notebook. But essentially, the derivative of... Actually, I can do this simple. So e of x, we've got the derivative of e of x, right? E of x, here we go. That is an exponential. The derivative actually becomes... it becomes the first function, so e of x times the derivative of the exponent, which is in this case x, so we have dx over dx, which equals 1, right? Times the natural log of the base. The natural log of e of x is 1. So we cross that out, 1. You see that? So that is what you do for any exponential, though. So the derivative of e of x is just e of x, and we just proved that. However, what about a to the x, right? A being any number. The derivative of a to the x is a bit different. We get a to the x times the derivative of x over dx, so that also equals 1, right? As we can see right there. Times the natural log of a. Now the natural log of a, because a could be any number, is not 1. Therefore, the derivative of a to the x becomes a to the x natural log of a, and that is the derivative of an exponential. That works for any exponential. You can do chain rules for exponentials. Again, that's just more complicated stuff. If you want to know that, you can look it up on your own. This is just meant to be a basic tutorial, which is also why we're not going over differential equations. We're not going over Hospital theorem or L'Hopital because... Yeah, and we're not going over Riemann sums. Riemann sums aren't hard per se, but they aren't basic calculus. They are when you can't take an integral, you look at a graph and you kind of add everything in the graph. So we're not doing that either. We will, however, explain derivatives. So why would you want a derivative? Well, you can use derivatives for a couple of things. Like, just how you can split up an equation to find zeros on a graph, and you can use an equation to find where the function, everywhere the function hits, where it's going to peak, you can use derivatives to find the extrema, right? So in the case of x squared, is x squared a good example? Yes. So in the case of x squared, the derivative is 2x, right? So the 0 of the derivative is where the function has a max or a min, so an extrema. So the derivative of x squared is 2x, and 2x equals 0 when x equals 0. Therefore, x squared has an extrema at 0. Right? You can then look at the function, figure out whether it's going up and down. Since x squared is positive, that means the graph is coming up from the bottom and going, no, the graph is coming down and then going back up, because that's an x squared graph. Because it's an even exponent, it goes down like this, it goes up like that. So x squared loops, it actually hits the x-axis. That does not have to do with calculus, that's more pre-calculus and algebra 2. So if you want to know that, you got to do that on your own. However, we now know that the extrema is at 0. Now, there's other ways you could have done that. The other ways are harder because calculus is really easy to use once you know how to do it. Then you can actually find inflection. So just like how you can take the derivative of a function, you can take a second derivative, which is the derivative of the derivative, or the rate of change of the rate of change. How is the... Yeah. And where that equals 0 is every possible place the graph has a point of inflection. Sometimes it's got an asymptote, right? When there's an asymptote at that point, it does not equal, it's not going to have a point of inflection there. That just happens to be how it is. Yeah. Why would you use calculus? Honestly, you're probably not going to use calculus. That is my basic tutorial to calculus, how to use calculus. However, chances are you're not going to use math in general, or the math you're going to use is statistics. Calculus is mostly used in physics, I'm not going to lie. So unless you're going into physics, chances are you're not going to use calculus. And yeah, where would you use calculus though? Well, for example, let's say you drive a car. I don't know if you drive a car. I don't care if you drive a car. However, let's say you drive a car. A car moves. When a car moves, it travels a distance, right? Let's say my car went from point A to point B. Now, we want to know how fast it's going, so we can take the equation for the position at a point, and we can take the derivative of that by putting in the value of the point. So let's say our car is at 4 meters. We want to know our car traveled 4 seconds, right? The function is x to the third. So the derivative, so putting 4 seconds in, so that is 4 to the third, which is 64, which means our car traveled 64 meters in 4 seconds. Now, we can take the derivative of that to get 2x squared. Now, evaluating that at 4 seconds gets us that 4 squared is 16 times 3 is 48, which means our car is traveling 48 meters per second at the point of 4 seconds. And then you can use it to find the acceleration of the car, which is how fast the car is speeding up or slowing down. So the derivative of 3x squared is 6x. Evaluated at 4 seconds is 24 meters per second squared. So the car is accelerating at 24 meters per second squared. That is how you would typically use calculus. You can also use calculus to help math, because calculus makes math a lot easier. It is really simple, too. It is like basic calculus is really simple, as I just taught it in, I don't know, maybe 30 minutes. I don't know how long this recording is. Calculus, now there is a lot harder calculus when you get into parametrics, you get into differential equations. It does get harder. You get into Euler's method. All of that is harder, like rotating a graph around an axis. However, chances are you're not going to use that. Chances are you're just going to use basic calculus, which is why I made a basic calculus tutorial for anyone that wants one. limits are annoying, but calculus is usually used as an equation evaluated over time, as I just explained with physics. It isn't always, but if you want to know how, if you want to learn calculus-based physics, look at Physics C, mechanics and Physics C, electricity and magnetism. That's on you to do, but that is my tutorial. Thank you for watching my tutorial. This is a calculus assignment, my calculus artifact, that, as I said, didn't go so well the first time. I still want to make a game. However, I don't know if I'll be able to, so this is essentially what my game was going to do. Without me explaining it, it was going to have little hint notes, and you were going to use calculus to open up paths to leave a castle. Programming is hard to learn when you haven't taken a coding class. We'll just say that. If I end up coding the game, I will show Miss Rieger by next year. I will show, I will probably post the game for free on Steam, because why not? But not going to get our hopes up, because I tried Python, I tried Wolf RPG, and I am extremely lazy if I don't have to do something. So like, I don't know if I'm going to end up finishing it now that I've finished this project, but I was trying to learn those softwares, and I looked it up, and I've been doing this project for some 4 or 5 weeks, and it takes 10 weeks to get a decent understanding of Python, and Wolf RPG is harder to use. So I decided that I was not going to do that, and I apologize for having this artifact be so late. And if I knew that coding was this hard to learn, which I don't know why I thought it would be easy to learn, I would have done this right off the bat. Thank you for watching my video. I hope this tutorial helped you understand calculus and how to use the basics of it. If you want to look into it, there is stuff online. And yeah, thank you. Bye.